Hi, this lesson is about derivatives of trigonometric functions. And we'll also do a little bit of work on limits later in the lesson. So before we talk about derivatives, let's just review some basic concepts you should know about trigonometry. And that is that all six of your trigonometric functions can be expressed in terms of one or more of the other trigonometric functions, like sine of x is equal to 1 over cosecant of x, and also cosecant of x is equal to 1 over sine of x. So basically, sine and cosecant are reciprocals of each other. Same relationship between cosine and secant. Cosine of x is equal to 1 over secant, and secant of x is equal to 1 over cosine of x. And tangent and cotangent, well, those are special because not only are tangent and cotangent reciprocals of each other, but tangent can also be written as sine of x over cosine of x, and cotangent of x can be written as cosine of x over sine of x. So in addition, you should be familiar with the three trigonometric identities based off of the Pythagorean theorems. Sometimes these are called Pythagorean identities. And that is that sine squared of x plus cosine squared of x equals 1. Tangent squared of x plus 1 equals secant squared of x. And 1 plus cotangent squared of x equals cosecant squared of x. So sometimes you have to make substitutions based on these trigonometric identities. So I'm just reminding you of those. Also, you should remember how to convert from degrees to radians and from radians to degrees. So to convert from degrees to radians, you have to take your degrees and multiply it by pi over 180, and that will give you radians. And to convert from radians to degrees, you take your radians, multiply it by 180 over pi, and that will give you degrees. You should also know a couple of common triangles. And those triangles are your 30, 60, 90 triangle, as well as your 45, 45, 90 degree triangle, and the relationship between the sides. Just again, to remind you, you can rewrite 30 degrees in terms of radians. 30 degrees is the same as pi over 6, and 60 degrees is the same as pi over 3. So the three sides of the triangle are 1, root 3, and 2. Remember that 1 is always opposite of the 30 degrees, and the root 3 is always opposite of the 60 degrees. So even if 30 degrees and 60 degrees are flipped, meaning 60 degrees going here and the 30 degrees going here, then the 1 and the root 3 would switch as well. But the hypotenuse remains as 2. So remembering that your 6 trig functions are based off of two sides of a triangle, sine is opposite over hypotenuse, so sine of 30 degrees is 1 over 2. Cosine of 30 degrees, that's adjacent over hypotenuse, so that's root 3 over 2. Tangent is opposite over adjacent, so that's 1 over root 3, but if you rationalize it, multiply top and bottom by root 3, you get the tangent of 30 degrees is root 3 over 3. And then the other three trig functions are just reciprocals of these. So cosecant of 30 degrees would be 2. Secant of 30 degrees would be 2 over root 3. And cotangent of 30 degrees would just be the reciprocal of this, which is just root 3. But if you look at these trig functions with the perspective of 60 degrees instead of 30, the sine of 30 degrees, again, that's opposite over hypotenuse, that's root 3 over 2. Cosine of 60 degrees, that's adjacent over hypotenuse, that is 1 over 2 or a half. And tangent of 60 degrees is opposite over adjacent, so that is root 3 over 1, which is just root 3. Okay. And again, the other three trig functions, cosecant, secant, and cotangent, would be reciprocals of these numbers. All right, and then looking at the 45, 45, 90 degree triangle, That one's a little bit easier to remember because it's an isosceles right triangle, meaning the two legs are equal. So your legs are root 2 and root 2. Your hypotenuse is the same as in the 30, 60, 90. It's still 2. So sine of 45 degrees is opposite over hypotenuse. That's root 2 over 2. Cosine is also root 2 over 2. And tangent is opposite over adjacent, so root 2 over itself is just 1. And don't forget that you can rewrite 45 degrees in radians as pi over 4. Okay, so knowing these basic angles will be really helpful to you, as well as these angles as you move into other quadrants. So 30, 60, and 45 degrees, those are all acute angles, therefore they are reference angles, but these triangles can actually exist in either quadrants 1, 2, 3, or 4, which means that the signs, plus or minus signs of these trig functions will change as you move around your quadrants. And so here's just a reminder of what the graphs of your trig functions look like. So this is your sine function here. It starts at 0, then goes up to 1, back down to 0, and then down to -1, and so forth. And this oscillates forever on and on because the domain of sine is all real numbers. And then cosine starts at 1 and then goes down to 0. So it is a shift of the sine function by 90 degrees or pi over 2 radians. So it starts at 1, goes down to 0, down to -1, back to 0, back to 1. And again, this oscillates on and on forever. Tangent, remember tangent is the same as sine over cosine. So tangent is undefined everywhere that cosine is equal to 0. So cosine is equal to 0 at -3 pi over 2, at -pi over 2, at pi over 2, at 3 pi over 2, and on and on. And so that's exactly where you see your asymptotes here. I have an asymptote, which is this vertical line at -3 pi over 2, then again at pi over 2, and at pi over 2, and at 3 pi over 2, the same places where cosine was 0. And again, that graph repeats forever and ever with those asymptotes every pi units. Other than that, tangent is always increasing from left to right. And then if I go here to the right to cosecant, cosecant is the reciprocal of sine. So cosecant has vertical asymptotes everywhere that sine is equal to 0. So where is sine equal to 0? It's equal to 0 at -2 pi, at -pi, at 0, at pi, at 2 pi, etc., every pi units. And that's exactly where you see your vertical asymptotes here. So -2 pi, -pi, 0 pi, and 2 pi. And again, other than that, the graph looks like, they look kind of like parabolas. So these points, this is the point 1, this is the point 1, y value of 1, and this one has a y value of -1, this one has a y value of -1. And again, that will coincide where this is equal to 1 and where this is equal to -1, etc. Secant has a similar relationship as cosecant had with sine, but secant has a relationship with cosine. So secant has asymptotes everywhere that cosine is equal to 0, and cosine is equal to 0 at -3 pi over 2, and -pi over 2 at pi over 2, and at 3 pi over 2, and many others from there. It goes on and on forever. And that's exactly where you see your vertical lines here. And then cotangent looks really similar to tangent, except the graph is always decreasing from left to right. And this time the asymptotes exist everywhere sine is 0, because cotangent is cosine over sine. Can't have 0 in the denominator, so it's undefined. So everywhere that sine is equal to 0, you'll have vertical asymptotes here in your cotangent graph. So knowing these graphs is helpful. We've used them in the past when evaluating limits. So you should just get more familiar with them if it's not something you remember from trigonometry. Okay, so now let's move on to derivatives. So just like the other rules that we've learned in the past, there are 6 rules for derivatives that you're going to want to memorize. The more readily available these rules are in your mind, the easier this course will be for you moving forward, as well as future calculus courses and differential equations and other math courses that you might need to take, as well as physics. So the derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent of your variable is secant squared of the variable. Derivative of cosecant is negative cosecant cotangent. Derivative of secant is secant x tangent x. And derivative of cotangent is negative cosecant squared. All right, so it takes some time to kind of get used to these and not mix up the plus or minus signs because some of them have negatives in front of them. So just the more you practice them, the better you'll get at it and then actually make an effort to memorize them. All right, so here's our first example. You're given y equals x squared cosine of x, and we want to find y prime. Well, this is a product of 2 functions, x squared and cosine of x, so we have to use product rule. So here's our setup. I'm going to let f equals x squared, g equal cosine of x, f prime is 2x, you have to use power rule, g prime is negative sine of x, again that comes right from here, and then you just plug it into your product rule. So I did f g prime plus g f prime, and then I just put the negative in front of the first term, because the whole thing is negative, so it's negative x squared sine of x plus 2x cosine of x, and you are done with that problem. Okay, let's move on. This time we need to evaluate our derivative at a value, which is pi over 4, and our function is 6 secant theta. All right, so we know that our secant derivative is secant tangent, but our variable here is theta. So f prime is 6 secant theta tangent theta, and then we're ready to substitute in pi over 4, which is what you see here. All right, so now we have to evaluate it. So remember, pi over 4 is 45 degrees. We just talked about this special type of triangle. And so secant is the reciprocal of cosine. Cosine of pi over 4 is root 2 over 2, so this one will be 2 over root 2. And tangent of pi over 4 is 1, so you're left with 12 over root 2, and when you rationalize it, you multiply numerator and denominator by root 2, leaving you with 12 root 2 over 2, but 12 divided by 2 is 6, so f prime of pi over 4 is 6 root 2. All right, let's do another one. This time we want to find the equation of the tangent line to the graph of y equals negative 4 sine of theta at theta equal to pi over 3. All right, so in order to find the equation of a line, you need a point and a slope. So I don't quite have the point, I just have the first part of the point. I need to know what the y value is. So that's the first thing I computed. I plugged in pi over 3 into the original function. Sine of pi over 3, that is a 60-degree angle, that is root 3 over 2. And when you simplify it, you get that y is negative 2 root 3. So this is our point that we will be using soon. But I also need to find the slope. And remember, the slope is the derivative. The slope of the tangent line to a curve is the derivative. So the derivative of negative 4 sine of theta is negative 4 cosine of theta. So now we compute what that value is at pi over 3. Cosine of pi over 3 is a half, so it's negative 4 times a half. So my slope is -2. So now we're ready to use our slope and our point and plug it into the point-slope formula, which is what you see here. So I have y minus -2√3 equals -2 times theta minus pi over 3. So on the left side, you get y plus 2√3. On the right side, you distribute -2, so you have -2 theta plus 2 pi over 3. And then solving for y means you subtract 2√3. So your final answer, your equation of the tangent line is -2 theta plus 2 pi over 3 minus 2√3. So these last two numbers are both irrational numbers. You really can't combine them because one has that radical there. So you can leave it as is. Anything else would just be an estimate, which we do not want. We want an exact answer. Okay, so here's another problem where we're asked to find the derivative, and you're given that y equals tan of x over x cubed. So our function is a quotient, so we need to use quotient rule. So we're setting that up here. I'm letting f equal tan of x, and with quotient rule, the numerator will be f, the denominator will be g. Your f prime is secant squared of x. Your g prime is 3x squared. And then we just have to plug it into the formula. So with quotient rule, you have to start with the g and the f prime. So that's what I did first. I have x cubed times secant squared of x, and then minus, that's the formula, minus f g prime. So that's tan of x times 3x squared all over g squared. So it's x cubed to the second power. All right, so in the next line, I factored out an x cubed because that's a common factor between the two products in the previous line. That leaves me with x squared times x times secant squared of x minus 3 tangent of x. By the way, these x's cannot be combined because tan of x is the input or the angle to tangent, so you cannot combine that with the 3x squared. All right, so when you factor, you get this line here, and then in the next line, I actually can cancel the x squared in the previous line with 2 of the x's in the denominator, so my denominator becomes x to the 4th, and my numerator is x secant squared of x minus 3 tangent of x. All right, so as I mentioned at the beginning, there is a brief lesson on limits that has to do with trigonometry. So before I give you a new rule, we're just going to practice evaluating a limit here by direct substitution. So we can apply direct substitution in this problem because sine and cosine has no restrictions to the domain. So pi over 6 is something you can just evaluate by direct substitution. So the first thing I did was I factored out the 1/8, kept it separate from the limit. And then I just have to evaluate the limit of sine x, cosine x as x approaches pi over 6. So when you apply direct substitution, like I do here, you no longer write your limit, and now we're just ready to evaluate those two functions. So pi over 6 is a 30-degree angle. The sine is a half. The cosine of pi over 6 is √3 over 2. So when you multiply those three fractions together, you get √3 over 32 as your limit value. Okay, but there's a really handy definition that we can use in some instances that has to do with sine, but it has to be in a very specific format. So if you're evaluating the limit as x approaches 0 of sine of x over x, that is equal to 1. So you can accept this as true. It's a definition. But the reciprocal is also true. The limit as x approaches 0 of x over sine of x is also equal to 1. So remember, you wouldn't be able to just plug in 0 here because it would be undefined. So the function is undefined at 0 in both cases. This would also give you a 0. But the limit exists. As you know, that happens. It's a possibility. All right. So let's see how we can use this. So I want to evaluate the limit as x approaches 0 of sine of 9x over x. So that looks sort of like this, except that 9 is a problem. You cannot, so this is just a warning because I've seen people do this over the years. This is not true. You cannot factor out anything from the angle or the input value. So you can't just get rid of the 9 like that to make it look like the definition. But what I do need is for my denominator and my numerator to have both the same angle. So the input angle for sine and my denominator have to match. So how do I make that happen? I make that happen by multiplying numerator and denominator by 9. So remember, that's just equal to 1. So when you multiply something by 1, you're not changing the value of the function. You're just making it look a little different to suit your purposes. So if I multiply numerator and denominator by 9, I get the next line, which is 9 sine of 9x over 9x. And then I'm going to factor out this 9 to the front, which is what I did in the next line. So I have 9 times the limit as x approaches 0 of sine of 9x over 9x. Well, now my angle and my denominator are the same, and that means I can apply my definition above. The limit as x approaches 0 of sine of 9x over 9x is equal to 1, which is what you see on this next line. And so your limit value is just 9. Okay, so let's practice another one where we're applying that definition. Here I have the limit as theta approaches 0 of 3 theta over sine of 5 theta. So similar to the last example, I have something different in my numerator than what this input angle is. So, and I need for them to look the same. So first thing I did was I moved the 3 out of the way so that I just have theta over sine of 5 theta. Then it looks similar to my first example in that all I need to do is multiply numerator and denominator by 5, which is what you see here, which gives me the next line. I have 3 times the limit as theta approaches 0 of 5 theta over sine of 5 theta. Then I'm going to move this 5 out of the way because we really don't need that, which is what you get here. So I have 3/5. The limit as theta approaches 0 of 5 theta over sine of 5 theta. Now that looks like our definition. This part right here looks like the second part of the definition, the reciprocal. What that's equal to 1, which is what you see on the next line. And so your answer is just 3/5. All right, here's another. We want to evaluate the limit as x approaches 0 of x over tangent of 3x. Now this one looks quite different because the definition that I gave above has to do with sine. This one has a tangent function in it. I cannot apply direct substitution because tangent of 0 is 0. So I need to find another way. So I'm going to use what I know about tangent. Tangent can get rewritten as sine over cosine. But tangent is in the denominator, which means it's basically cotangent. So I'm going to rewrite tangent as cosine over sine. So remember to keep the input as 3x. All right, so now I can see that I have a sine of 3x somewhere in my problems, which means I am going to be able to use that definition that I gave, but I'm going to split it up so you can see what I'm doing. So I can rewrite my limit into 2 separate limits. I'm going to keep the x over sine of 3x together and separate out the cosine of 3x. So if you look back to one of our earlier lessons, I believe it was 2.5 or 2.3, when we talked about limit laws, you can rewrite one limit into multiple limits the way I did here at this line. But this first limit, the x over sine of 3x, I can't quite use the definition above because I'm missing a 3 in the numerator, which is why I'm multiplying numerator and denominator by 3. and then the other limit is fine. The cosine isn't going to cause us any trouble because I can evaluate cosine at 0. So then I get this line here, I get 3x over 3 sine of 3x. I'm going to move this 3 out of the way so it becomes 1/3 the limit as x approaches 0 of 3x sine of 3x times, and then here I'm already applying direct substitution and plugging in the 0. Well, this limit is just the definition above. We know that's equal to 1. So I have 1/3 times 1, and cosine of 0 is 1. So your answer is just 1/3. All right, so that's it for that lesson. Give the homework a try. Good luck.